Go.
Okay, today during lecture, we'll be going over reactions of simply supported beams. What you're going to need for this lecture is your types of support handouts, which we went over last week. So if you guys will all get that out, that'd be great. And also you're going to have to remember your equations of equilibrium, which we've been ramping up to for the last month. This involves your forces in the vertical direction, your forces in the horizontal direction, and your sum of forces rotating. We're going to be going over a simply supported beam with a centered load. This is the most simple type of beam there is. As you can see, there's a load P centered on the beam, L over 2 from each reaction, and a total length of L. At end A, you have a pin support. At end B, you have a roller support. Now, if you pull up your handout, your nice little handout, and look at pin support, you're going to see the description. And if anyone can recall from last time, a pin support doesn't allow for movement in the X or Y directions, so you're going to have two reactions there, one a horizontal reaction and one a vertical reaction. But it allows for a moment, so there will be no reaction for a moment. And a roller support prevents movement in the vertical direction only. So the only reaction you're going to see at the end B of your roller support is a vertical reaction. There will be no horizontal reaction and no moment. So if we go back here, back to our simply supported beam, with our pin support and a roller support, we're going to see two reactions right here at the pin support. One in the horizontal direction and one in the vertical. As you guys notice, I set a coordinate system with up and to the left as being positive. So we're going to stick with that throughout the whole problem. Now if we look at the roller support, as per our handout, it says that the only type of reaction that you're going to find is in the vertical. So we're going to have reaction By as in the vertical. To solve for our reactions, because that's the whole setup for this, so we're going to use our equilibrium equations, which is the sum of forces in the y must be equal to 0. The sum of forces in the x must be equal to 0. And the sum of moments about some arbitrary point that we assign must also be equal to 0. So if we look at the sum of forces in the y right off the bat, we have three vertical forces, three of them. One, reaction AY. We have reaction By. These are our only two positive forces. We have one negative force, which is the load, P, coming down at the center of the beam. So if we put these into our equilibrium equation for sum of forces in the vertical direction, we're going to have reaction AY plus reaction By minus P equals 0. Now, I see a problem here. We have two unknowns, one known, and one equation. So we have two unknowns and one equation. We can't solve this right now. So let's go ahead and look at sum of forces in the x. Okay? We have one horizontal reaction going in the positive assigned direction, and that's R of AX. So right off the bat, we can see that R of AX equals 0. So we have one force solved for, R of AX. If we had another force coming in somewhere, coming from a horizontal direction, that would change this. But as of right now, it's just 0. We're going to look at moments. We got to pick some point on this beam, anywhere. It could be any point in reaction, middle of the beam, wherever you want to take moments about. We're going to take moments about end A. As you can see, a moment is defined, remember from last couple lectures, as a force through a distance. So our force here, generating a counterclockwise rotation, RB times the entire length, is 1 moment. So you have your force times your moment arm. The applied load P generates a negative moment, which implies that it's going in the clockwise position. So if you look at the beam and you have a P coming down, it's causing the beam to rotate clockwise around point A. Remember this from the last couple lectures we went over. And that moment arm for P is acted on half the length of the beam, so L over 2. If we solve this for our reaction of By, we get this, we're going to take this and throw it back into our sum of forces in the y direction. So we're going to be able to solve for R of AY as well. You can go through the derivations. These slides will be posted online on Blackboard if I'm moving too fast. So that's R of AY. So in recap, these are all our forces. We got an R of AX, which was a simple reaction we found from our sum of forces in the x direction, which is 0. Our sum of forces in the y direction, in addition to using the sum of moments equilibrium equation, we were able to deduce R of AY and R of BY. And we're going to solve this problem. So instead of taking, let's go ahead and establish a coordinate system and draw out our reactions. So a coordinate system, just an arbitrary one that's generally accepted by everyone, is upwards is positive, to the right is positive. So let's go ahead and take our simplest equilibrium equation and solve for forces in the horizontal direction. So we have a horizontal force here, which is AX. We have a vertical force here, which is AY. And we have one vertical force here, which is BY. To solve for forces in the x direction, we're going to sum the forces in the x direction, taking right to be positive. We're going to set that equal to 0. That's what our equilibrium equation says. The only force we have in the horizontal direction is AX. So AX equals 0. Let's go ahead and take a moment. This time, instead of taking a moment about point A, let's go ahead and take our moment about point B. So if we do that, we're going to sum our moments about point B, taking counterclockwise to be positive. That's going to equal 0. So if these are moment, where we're going to take our moment, this force disappears. We don't take into account this force. So we're going to have two forces to take into account. This force disappears as well because it's acting in the same line as B. This force is actually acting right on this B, so it doesn't generate any moment. So our first force we're going to encounter is our load. We're going to have our 16 kip force coming down a distance of 10 feet from B. Now let's say, is that going to produce a positive moment or a negative moment? This force is causing the beam to spin counterclockwise, so it's going to be positive. Because what we established as our positive direction is counterclockwise. Our next moment, or our next force is A. So we have AY acting a distance of 14 feet from B. Now is AY going to be a positive or negative moment? AY is causing this beam to rotate clockwise. We said counterclockwise is positive, so this is going to produce a negative moment. If we go ahead and solve for AY using our basic algebra skills, we're going to get 11.4 kips in the vertical direction. So we've got force AY. The only force left to get is force BY. So let's go ahead and sum forces in the vertical direction. Our last equilibrium equation. Taking upwards to be positive. So we have three forces that act in the vertical direction. We have AY. AY is acting upwards, which is positive. We have our force, P, which is acting down. Down is negative. Negative 16 kips. We have By, which is acting upwards. Upwards is positive. If we substitute our Ay, which we found using our moment equilibrium, into this equation, we're going to get a By of 4.57 kips, acting upwards. So those are our 3 support reactions. Pretty easy, not bad at all. Same process for all beams. Things might get a little trickier. We might throw a hinge in there at you. We'll wait a couple weeks for that. I'll post some problems similar to this on Blackboard. If you guys want to take a look at them for homework, they'll be due next class. If you guys have any questions, feel free to come in during office hours. If not, have a good rest of your day.